have been discussing the JWKB approximation and have given the solutions of the JWKB in the JWKB approximation of the differential equation. Today we will continue our discussions on that. We will consider one small problem in tunneling probability calculation. Actually, we will assign a problem, and then we will discuss the generality of the WKB approximation, and we will show that it can be used to solve a general class of differential equations. Finally, we will give a heuristic treatment of the justification for the connection formulae. So, first we will start with the tunneling through the barrier problem, which we had discussed in considerable detail, and we had considered a potential energy variation which was something like this. So, this is the V of x, a particle of energy E of mass mu is incident, and this is the energy level, and there were two turning points. Now, the k square of x is equal to 2 mu by h cross square E minus V of x. So, since it is the inverse of minus sign of x, so k square of x, this is the variation of k square of x, and x is equal to a and x is equal to b are the turning points. So, here you will have oscillatory solution, here you have exponential solutions, and here you have again oscillatory solutions. So, what we did was in region 3 we wrote down a solution like this: a under root of cup k sine of integral b to x k dx plus pi by 4. Actually, we wrote the solution, we can write down the solution as sine and cosine. So, instead what we did was we considered an outgoing plane wave. So, we had exponential I times this. So, actually I should write it down as e to the power of I integral b to x k of x dx plus pi by 4, and wrote it as cosine plus sine, then used each of them to hop from this turning point here, and then we looked at the turning point x is equal to a, and then when we hopped through this turning point and obtained solutions here, and the solution in the region 1 was expressed as an incident wave plus as a reflected wave, and we compared the coefficients, and we found out that the transmission coefficient was equal to e to the power of minus theta square, where theta was equal to exponential. So, I am sorry, the transmission coefficient was theta square, and theta was equal to exponential minus a to b kappa of x dx, because in the region a to b k square of x is negative, and so therefore, we define kappa square of x, which was equal to minus k square of x, and using that and therefore, using this relation we discussed the 2-3 problems. One, the tunneling through a parabolic barrier, then we discussed the tunneling through the triangular barrier, and also then the alpha decay problem. What I wanted to tell you today is that if we have a double potential like this, and which has 2 peaks like the one that I have shown here, and I assume an energy E and the V of x is variation like this, then the corresponding k square of x, which is given by k square of x, is once again 2 mu by h cross square E minus V of x, and it will be something like this. So, there will be 4 turning points now. Now, then what we have to do is we have to first start with the solution in the region 5. So, psi in region 5 will be an outgoing wave. So, we write down this as f by root k e to the power of I integral b to x k dx plus pi by 4. Okay. So, I write this solution here, which I write as f by root k cosine of the same argument, cosine of this argument. So, let us suppose this is say I write as capital phi plus I times sin phi. Okay. And then use connection formulae to go to region 4. Then we look towards the turning point A, and I go over to region 3, and then we look to turning point minus A, and then use the connection formulae to get to region 2 and then to region 1. It is a very systematic process, very straightforward process, and I would urge all of you who want to learn the tricks of using the connection formulae, work this out yourself. It will help you to use the JWKB approximation with tremendous efficiency and simplicity. It is very simple. You just have to get used to using these connection formulae. And finally, in region 1, you express the solution as A times the coefficient of the incident wave plus e to the, and then you have the B, which is the coefficient of the reflected wave. And then you will have f by A whole mod square will be the tunneling probability, and if you calculate that, you will find that the tunneling probability comes out to be, let me write this expression, if you have a double hump thing, and these are the 2 turning points minus A, minus B, plus A and plus B. This is the V of x variation, this is the V of x variation as a function of x. So, if you work this out, and I would urge all of you to work this out, the tunneling probability comes out to be 4 by 4 sin square alpha plus 4 by theta square plus theta square by 4 cos square alpha, and a similar expression for t, and you will find that r plus t is equal to 1. So, that the reflection coefficient is 1 minus t. What are the values of alpha and theta? The value of alpha is minus A to plus A, sorry, this is minus A and this is minus B, I am sorry. So, you have here, let me do this here. So, this is minus A and this is minus B. I hope all of you can see this, So, the transmission coefficient becomes, so the alpha is equal to minus A to plus A, and between minus A and plus A, k square of x is positive. So, this is k of x dx, and then theta is defined to be equal to exponential minus A to B kappa dx. As I mentioned to you, you first start with an outgoing plane wave here, then you hop to this region, 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 and in each hopping you use the JWKB connection formulae. The remarkable feature of this simple formula is that when alpha is equal to n plus half pi, when alpha is equal to n plus half pi, then cos square alpha is 0, sin square alpha is 1. So, t is equal to 1. These are known as the Fabry-Perot transmission resonances, Fabry-Perot transmission resonances, and no matter what the shape of the potential variation be, the transmission coefficient is unity. These correspond to this is alpha is equal to n plus half pi. These are the eigenvalues corresponding to the well. So, those energy eigenvalues which form for this particular well, you have transmission resonances. These are the modes which resonate back and forth between the well, and you have an unity transmission coefficient. So, to conclude that for a double hump potential well of the type shown here, you have double. So, I would advise all of you to work out step by step the tunneling probability. It is the details. If you are unable to do that, the details are given in our book by myself and Professor Lokanathan on quantum mechanics, 5th edition. So, the details are there also, but I would like you to work this out and obtain an analytical expression for the tunneling probability, and this tunneling probability becomes equal to 1 irrespective of the shape of the potential structure when alpha becomes equal to n plus half pi, and those are known as the Fabry-Perot transmission resonances. Now, we then go over to calculating, justifying the connection formulae, For example, if you have a k square of x variation like this, this is the k square of x variation, and you have a 0. So, that on the right side of the turning point you have exponential solution, and on the left side k square of x is positive. So, we have sine and cosine solution, and we had said without proof that 2 by root k, let us suppose the turning point is x is equal to a, then 2 by root k sine of x to a k dx plus pi by 4 goes over to an exponentially decaying solution minus exponential minus a to x kappa dx. And similarly, we had 1 over root k cos of x to a k dx, k of x dx plus pi by 4. It goes over to the exponentially amplifying solution. So, 1 over root k exponential plus integral a to x kappa of x dx. Now, I want to justify this. Now, near the turning point, I can assume that the variation of k square of x is linear. So, the equation that we have been wanting to solve is d2 psi by dx square plus k square times psi of x is equal to 0, k square of x, actually k square of x. Now, we assume that in the vicinity of the turning point, so at x around x is equal to a, we assume that k square of x, in this case it is a decreasing function of x. So, we say that this is equal to minus alpha of x minus a approximately. So, that in the vicinity of the turning point we assume a linear variation for k square of x. So, therefore, my Schrodinger equation or the wave equation becomes d2 psi by dx square minus alpha into x minus a psi of x is equal to 0. Now, I make a transformation. That z is equal to alpha raised to the power of 1 by 3 into x minus a. Then d psi by dx, will be d psi by dz into dz by dx, that is alpha to the power of 1 by 3, then alpha to the power of 2 by 3, and then you will have x minus a z by alpha to the power of 1 by 3, and so on. You do that and you will obtain d2 psi by dz square minus z psi of z is equal to 0. This equation is known as the Airy equation, after the name of the British astronomer G.B. Airy. This is, and the solution of this, the rigorously correct solutions of these equations are known as the Airy functions. Now, first let me write down. So, here in this case k square of z is equal to minus z. So, for z greater than 0, I must write k square of z is equal to minus kappa square of z, and kappa square of z will be equal to plus z. So, that for z greater than 0, this equation becomes d2 psi by dz square minus kappa square of z psi of z is equal to 0. Now, since kappa square of z is equal to z, so kappa of z is square root of z, and square root of kappa z is equal to z to the power of 1 by 4. Now, the WKB solutions of these equations are 1 over under root of kappa exponential plus minus integral z kappa of z dz. So, if I integrate this kappa of z dz, this will be exponential plus minus 2 by 3 z to the power of 3 by 2, and outside it will be z to the power of 1 by 4. Therefore, the of this equation d2 psi by dz square minus z psi of z equal to 0. As z tends to infinity, the JWKB solutions are, z tends to plus infinity, the JWKB solutions are plus minus 1 over z to the power, actually z to the power of 1 by 4 exponential plus minus 2/3 z to the power of 3 by 2, small z everywhere. Now, for z less than 0, this is positive, minus z is positive. So, I must write it as d2 psi by dz square plus k square of z is equal psi of z equal to 0, where k square of z is defined to be equal to minus of z. And then as z tends to minus infinity, the JWKB solutions are, 1 over mod z, because now it becomes minus z, mod z 1 to the power, and then sine or cosine, sine and similarly cosine, and 2/3 plus minus you can have mod z to the power of 3 by 2 plus phi. And similarly you can have the cos solutions. So of this equation, this is the, as I mentioned, this is the Airy equation, and of these Airy equations, the WKB solutions are exponential, this and that. Now, of the Airy equation, the rigorously correct solutions are denoted by AI of z and BI of z. These are known as the Airy functions, which are related to Bessel functions, Now, the Airy functions have the solid line. You see, actually this is not in terms of z, this is the solution of the equation d2y by dx square minus x y of x. So, please replace z by x. So, of ai of x, the two independent solutions are ai of x and bi of x. And ai of x has a asymptotic form as x tends to minus infinity, which is given by this. This I am not proving, but it can be obtained from the asymptotic forms of the Bessel functions, which must be known to all of you. Similarly, as x tends to plus infinity, this is the asymptotic form. If you can read properly, this is exponential minus 2 by 3 x to the power of 3 by 2. Now, these asymptotic forms are the JWKB solutions, and so therefore, the sine term goes over to this term. Let me first also show you the BI function. The other independent solution of this equation is the BI function, which are known as the Airy BI function, and the asymptotic form is a cos plus pi by 4 as x tends to minus infinity, and these asymptotic forms are plotted, if you can see this, as a dashed line. You see, the asymptotic solutions, which are just the WKB solutions, they go to infinity at x is equal to 0, because this is the turning point. X is equal to 0 is the turning point. So, here also the asymptotic solutions are shown by the dashed line, and they go to 0, and the asymptotic solutions are the JWKB solutions. Here the asymptotic solution of BI of x is actually, I should have written BI of z goes over to 1 over root pi z to the power of 1 by 4 e to the power of 2 by 3 z to the power of 3 by 2, and this also I should have written z. So, these are the same solutions that we had written down earlier. You see, exponential plus minus 2 by 3 z to the. So, one can say that cos plus pi by 4 goes over to 1 over root pi z to the power of 1 by 4 e to the power of 2 by 3 z to the power of 3 by 2. This suggests that since these are the WKB solutions, therefore, 1 over root pi k of z under root k of z cos of integral k of z dz. In this case, the turning point is at 0. So, from turning point say z to a, that is 0, and the turning point is say is a, this plus pi by 4 goes over to an exponentially amplifying solution. So, this is under root of kappa z e to the power of integral 0 to z, in this case therefore, a to z kappa z dd. So, this is the we have tried to justify the connection formulae, because what we did was we assumed the in the vicinity of the turning point the solution to be the variation to be linear. When we assume the k square of x variation to be linear, then the solutions are rigorously a I of x and b I of actually not x, b I of z, where z is equal to alpha to the power of 1 by 3 into x minus a. Then these are the WKB solutions, and we showed by comparing the WKB solutions with the actual, with the exact asymptotic forms, we found that the sign from x to 8 plus pi by 4 will go over to an exponentially decaying solution, and the cos term will go over to an exponentially amplifying solution. So, this is the justification. We assume this to be linear, then the solutions become Airy functions, and by looking at the asymptotic forms of the Airy functions and comparing it with the WKB solutions, we write the connection formulae. And as we have seen, if we use these connection formulae, we get exact results for the harmonic oscillator problem, and even for the linear potential it gives very accurate results. We calculated the tunneling probability using the lifetime of alpha particle decay, and showed the extreme variation. And there are many comparisons that have been made to compare the validity of the JWKB approximation, and it has been found that as long as k square of x, that is the potential energy variation, is reasonably smooth, then JWKB approximation gives a fairly accurate solution. We finally end up by saying that a general differential equation of the type p of x d2y by dx square plus q of x dy by dx plus r of x y of x dx equal to 0. I can always write this in the form of d2y by dx square plus f of x dy by dx plus g of x y of x. It is obvious that f of x is equal to q by p and g of x is r by p. Then we make two transformation. We make that, let us suppose psi of x is equal to y of x exponential half integral f of x dx. I leave it as an exercise for you, and if you assume psi of x to be given by this, and then you differentiate this and use this equation, you will find that d2 psi by dx square satisfies this equation, k square of x psi of x is equal to 0, where k square of x is now defined as g of x minus half df by dx minus 1 by 4 f square of x. So, what I was trying to tell you is that any second order differential equation of the type shown here can always be transformed to an equation of this type. Any second order differential equation of this form can always be transformed to an equation rigorously to an equation of this type, and then we can use the JWKB solutions to obtain approximate solutions of this equation. In fact, one can take the Bessel equation as an example and obtain solutions, and they often agree quite well with the exact solutions. So, first you look at any second order differential equation, try to transform it. Any differential equation of this type can be transformed to an equation of this type, and then one can obtain the WKB solution of that. So, in principle we have given a recipe for obtaining a JWKB solution of a second order differential equation of this type, and hence therefore the JWKB approximation forms a very powerful method for solving the second order differential equations. That concludes our discussion on the WKB approximation, in which, to summarize, this is a very powerful method for solving a second order differential equation in which k square of x is assumed to be a smoothly varying function. It should not be very rapidly varying, it should not have too many zeros, because if it has too many zeros, then you have to hop from one turning point to the other, but that in principle is possible as long as the variation of k square of x is fairly smooth, and therefore it has been extensively used not only in quantum mechanics, but in waveguide theory, in plasma physics, and in many other areas, diverse area of physics and engineering. Our next lecture, in this lecture itself, we will continue our discussions on developing an approximate method, and that will be the perturbation theory. We will continue our discussions on yet another very powerful approximate method, and the method is known as the time independent perturbation theory. So, we have here in the time independent perturbation theory, we write the Hamiltonian as a sum of two parts, h is equal to h naught plus h prime. Now, h naught is the Hamiltonian for which I know the solutions. So, h naught u n is equal to E n u n. For example, h naught may be the harmonic oscillator problem, like minus h cross square by 2 mu d2 by dx square plus half mu omega square x square. Now, of which we know the solutions. So, what are E n and u n? The E n we know that is equal to n plus half h cross omega, and u's of n are the normalized Hermite Gauss functions, the Hermite Gauss functions, or h naught may be the Hamiltonian corresponding to the hydrogen atom problem. Now, therefore, h naught is the portion of the Hamiltonian for which the solutions are known. Then we add to it another term, and then we try to calculate the effect of this term. So, for example, we have a charged oscillator, we put it in an electric field, and then there is a Hamiltonian which is something like minus say E times the electric field times x. So, this is the perturbation, or you may have something like the H naught may represent the hydrogen atom problem, in which it is given by H cross square by 2 m del square, or mu, actually mu is del square minus Z e square by r. This is V of r. So, for this problem we know that use of n is equal to r n l y l m. Actually these are 3 subscripts here. These are the wave functions. These are the wave functions. This n and this n are different. So, this may be something like, say, we may write as um or up. Up is a combined form of these 3, and the EP, the energy eigenvalues corresponding to the PS state, will be something like the energy for the first state divided by n square, and E1 is about minus 13.6 electron volts. So, I know the eigenvalues and eigenfunctions corresponding to H naught. Now, I put the hydrogen atom in a electric field, and there will be a perturbation, or in a magnetic field there will be an additional term which will represent the interaction with the electric field and the magnetic field. So, what will be the effect on the energy eigenvalues? This is an extremely important problem in quantum mechanics as well as in atomic and molecular spectroscopy. So, and in most problems of interest, you cannot obtain a direct solution of the a closed form solution of the Schrodinger equation, and we have to apply an approximate method. One approximate method we have already discussed, and that was the JWKB method, in which k square of x was assumed to be a slowly varying function. Here what we assume is that we have a solution which is known to us, which is close. So, the electric or the magnetic fields are weak enough, so that it makes a small change in the eigenvalue structure of H naught. So, what we do is the method involves in writing let me write it on a fresh page. So, our objective is to solve this equation, H psi is equal to W psi, where H I write as H naught, and I introduce a parameter G. If, for example, H prime is due to the perturbation due to the electric field, so it may be the parameter is something like the strength of the electric field. So, that when the electric field goes to 0, you have the original Hamiltonian. So, G is a parameter which is assumed to be less than 1. So, what we do is we make a parametric expansion of psi and W. So, our objective is to obtain a specific state, let us suppose the nth state. So, our objective is to find W n and psi n. However, we know the eigenvalues and eigenfunctions of the operator H naught. So, the solutions of this are known. So, H naught u n is equal to E n E u n. This we know. So, therefore, let me state the problem clearly. The hydrogen atom is put in an electric field or in a magnetic field. Because of the presence of the magnetic field, it causes an additional term, it results in an additional term in the Hamiltonian. If I exclude this term, then I know the solution of the eigenvalue equation corresponding to H naught. This may be something like the hydrogen atom problem or the harmonic oscillator problem or a particle in a box problem. So, these solutions, the solution of the eigenvalue equation corresponding to H naught are known to us. Our objective is that when we apply this perturbation, what will be the value of Wn and what will be the value, what will be the corresponding eigenfunction. So, what we do is we introduce the parameter g as I mentioned, and then make a parametric expansion, that is write psi n is equal to psi n 0 plus g psi n 1 plus g square psi n 2, etc. And similarly, we write W n is equal to W n 0 plus g W n 1 plus g square and so on. And I substitute this. So, this let be equation 1, this be equation 2, this be equation 3, this be equation 4 and this be equation 5. So, we substitute 2, 4 and 5 in equation 1. So, we get, please see this, H naught plus g h prime multiplied by psi n 0 plus g psi n 1 plus g square. Let me neglect the higher order terms right now, is equal to bracket W n is W n 0, the 0th order term plus the first order term multiplied by psi n 0 plus g psi n 1 plus this. Now, I multiply this out and collect terms of different powers of g. So, you have the term which is independent of g is H naught psi n 0 plus g will be H naught psi n 1, H naught psi n 1 plus H prime psi n 0 plus terms which are proportional to g square plus terms which are proportional to g cubed and so on. This will be equal to, the first term will be is equal to W n 0 psi n 0 plus the term which is proportional to g W n 0 psi n 1 plus W n 1 psi n 0 plus term which are proportional to g square plus terms which are proportional to g cube. Now, we let g tend to 0, and that is always possible because we let us suppose the external electric field goes to 0. So, then all the terms cancel out and we have the 0th order equation H naught psi n 0 is equal to W n 0 psi n 0. This is the 0th order equation, 0th order equation. And this is the same eigenvalue equation as the for H naught, because for H naught we wrote H naught u n is equal to E n u n. So, therefore, we first consider non-degenerate states. and I will tell you the difficulty that we encounter when we consider degenerate states. So, n is equal to 1 is this state, or n is equal to 0, then n is equal to 1 or n is equal to 1 and so on. Each state is a non-degenerate state. Then I can write this down immediately, that W n 0 is equal to E n and psi n 0 is equal to U n. This is the 0th order solution, which is obvious because there is no electric field or magnetic field or something, there is no perturbation. Now, then we have, so we said that this term is equal to this term. So, then these two terms cancel out, then we divide the whole equation by g. So, this goes out, this goes out, this goes out, this becomes g square and g. So, if I now make g tend to 0, then this is the first order term. So, the first order term becomes, please see, becomes h naught psi n 1 plus h prime psi n 0, which we have written as u n, w n 0 is E n, psi n 1 plus w n 1 u n. This is my first order equation. This is my first order equation. Similarly, I can write down my second order equation also, but we will restrict ourselves to only first order perturbation theory, because in most analysis one uses first order perturbation theory. Then what I do is that we have already assumed that we are considering the perturbation to the nth state whose eigenfunction is known. Psi n 1 I do not know, but I know that u n form a complete set of functions. Therefore, let us expand it psi n 1, we can always expand psi n 1 as a n 1 superscript represent that we are considering first order perturbation times u n. So, multiply this h naught, a n is a constant. So, h naught u n is equal to E n u n. So, h naught operating on this will give me summation a n 1 E sub n u sub n plus h prime u n is equal to E n summation a n 1. Actually, I am expand. So, I must put it here as m, because this is the dummy variable. So, this is a m 1 E m u m. I am considering the perturbation to the nth state. So, m n is fixed. So, this is a m 1 E n, a m n 1 and use of m plus w n 1 use of n. Now, I multiply by u k star and integrate, and I know that these eigenfunctions form an orthonormal set, that is u k star d tau is equal to the Kronecker delta function. You remember that the harmonic oscillator functions also satisfy this orthonormality relation, where the integration is over the entire space. So, therefore, if I multiply the entire equation by uk star, so we multiply the entire equation by uk star on the left and then integrate. So, the first term will become summation a m 1 E m delta k m plus h prime k n is equal to E n summation a m 1 delta k m plus W n 1 delta k n, where H prime k n is known as the k nth matrix element, is the u k star H prime u n d tau. Symbolically, this is more convenient to write this as k h prime ket n. This is the k nth matrix element of this. So, therefore, if I sum the series, only the m equal to k term survives, and so we have a k 1 E k plus H prime k n is equal to a n a k 1, because only the m equal to k term will survive, and W n 1 delta k n. So, case 1, if I assume that k is equal to n, that I multiply by u n star only. So, this term and this term cancel out, this becomes 1, and then W n 1 becomes H prime n n. So, this is the first order perturbation to the energy. So, this is u n star H prime u n d tau, and symbolically it is n H prime n in the bracket notation. When k is not equal to n, then you will have this term goes to 0, and if I take the others, so H prime k n is equal to E n minus E k into A k 1. So, you can use this, to calculate A k 1, which will be equal to H prime k n divided by E n minus E k. So, we have the coefficients, because psi n 1 was equal to A k 1 u k. Actually, we had written A m 1 u m. This is a dummy variable, so it does not really matter. But here, and this I will discuss in greater detail in my next lecture, one sees that if k is not equal to n, but E n is equal to E k, that is, if we have, let us suppose, a two-fold degenerate state, let us suppose this is the ground state, this is a two-fold degenerate state. So, this is U0, this is U1 and U2. U1 and U2 belong to the same energy state. So, that is a degenerate state. Then this tells us that H prime k n must be 0, and this I will explain in greater detail in my next lecture. That you see, in a degenerate state, if let us suppose U0 is a ground state and the second state is two-fold degenerate, then U1 is a possible wave function, U2 is a possible wave function, any linear combination is also a possible wave function. So, if that is so, then this relation E n minus E k times A k 1 is equal to H prime k n says that I must choose such linear combinations for which H prime k n, that is H prime 1 2 must be 0. That is, the representation should be such that the H prime in the subspace generated by the degenerate state vectors, the H prime must be diagonal, and then only the diagonal elements will give the energy eigenvalues. So, with that, if you have not followed this, we will give more illustrations. We will have, so the basic formalism is complete, that the first, the 0th order term is equal to E n, of course. So, these are the E0 and E1 and things like that, this we know. Then the first order correction Wn1 is equal to, you just have to calculate the matrix element. First we will do for non-degenerate states, and then we will say what precaution do we have to take for degenerate state perturbation theory. Thank you.